Yep. Okay, so welcome to the first kind of joint seminar between physics and IDAT. So we're happy to have Joao from CERN gives us a talk about the outreach activities of his group. Originally he worked at Lawrence Berkeley Lab for many years, 8 years, and then went directly to CERN. He started his outreach activities and for a while was in the Atlas experiment and then moved off into more outreach activities. Okay, please.
All right, thank you. So currently I'm the team leader and chief troublemaker of this beautiful thing we built 7 years ago at CERN called the CERN Media Lab. And I'm going to talk to you a little bit about well, the kind of science outreach we do there. But first, I think I should give you, whoops, working well. Technical problems, too much zoom. Sorry. What's going on? All right. So I thought I'll tell you a little bit about how we came about and give you a little bit of context about, whoops, all right, this is special. So perhaps I should introduce CERN first. Most of you maybe have heard about it. So CERN is an international organization. It's the European Organization for Particle Physics. It's an international organization like like the United Nations or the Red Cross. Only that our focus is science and more specifically particle physics. Not only, but mostly particle physics. So it has member states. Currently there are 22 member states, including the UK. And then there are also states which have different kinds of statuses, like observer status and associate members, and also cooperating non-members. So it's a huge international organization which has 2,500 employees and which is visited every year by around 12,000 visiting scientists from 120 nations and with affiliations to over 600 institutes. So CERN is perhaps more well known by its biggest project ever, which is the Large Hadron Collider. So the Large Hadron Collider is the world's largest particle accelerator. It has a circumference of about 27 kilometers. It crosses the French-Swiss border, and it's at a depth of about 100 meters. And of course, the LHC accelerates. Hello. The LHC accelerates particles and also heavy ions. A little bit more about that later on, and have some very special technological achievements were necessary to do this, including the achievement of the best vacuum in the solar system and the coldest temperature in the solar system as well. Well, all these gadgets are there for a purpose, not just to accelerate the particles per se, but to make them collide at specifically engineered points where we build detectors, which we pedantically call experiments. And so it's at these experiments that the physics happens. It's there that, well, so we want to break very tiny stuff, make them collide and see what comes out of their experiment. All right, so starting in the year 2009, which is the year where the LHC started its operations, we had quite a few peculiar challenges in terms of communication and outreach. You see, CERN is a research institution, a very big and prestigious one, but we were not in the business of, let's say, public relations and communication. However, suddenly the spotlight of the world was turned towards CERN. So we had a lot of milestones in the operation of the LHC. You know, like first beam of the LHC, the press was there. Record of energy, the press was there. A new record, the press was there. First collisions, the press was there. Then we had, of course, discoveries. Most notably, the discovery of the Higgs boson, which caused quite some activity in the media. Then, of course, with this came the prizes and awards. Here I have a picture of the Nobel Prize, which was attributed to Peter Higgs and François Englert, two of the theorists that predicted the Higgs boson, and also the other prizes like the prize Prince of Asturias. It's a very prestigious prize that is in Spain. And then, of course, suddenly CERN entered into pop culture. Oh my God. South Park made episodes which had CERN as a central part of the plot. There were novels, like most notably Angels and Demons, where CERN plays a very important part of the narrative. Hell, even Megadeth made, Megadeth, heavy metal band. They made an album called Super Collider. A little bit cut there, the slide. Super Collider, and this is a picture from the CMS experiment. Wow! Suddenly, everyone was talking about CERN, and of course, there were also the prophets of doom and gloom that were talking about the famous black hole that would end the planet and maybe the universe and beyond after we started these dangerous experiments, and all kinds of people spewing a lot of uninformed nonsense. But all of this forced us to create a new approach to how we communicate with the public, and to synergize our efforts and specialize in specific ways to transmit the information. So in the context of this, there was a team which was created with the objective of conceiving, developing, deploying amazing multimedia for this purpose of communicating science. There are many other ways to do this. There are teams that deal with press, teams that deal with narrative, and the team of the Media Lab was conceived specifically for multimedia and visual and interactive stuff. So this is the original Media Lab team. So it's a team made out of physicists or recovering physicists in my case. Like you can be a recovering drug addict or a recovering alcoholic, I'm a recovering physicist. Engineers, designers, technicians, and this team has evolved quite a bit over the time. And actually this slide is wrong. I say current hardcore, it's not really true. This is the current hardcore photo, the most current hardcore photo of the team. This was the team about a year and a half ago. Every year we receive new students, they rotate quite a bit. Students and fellows and so on. So right now we are a team of about 5 people as well, but we have collaborations with a few other institutes which do projects with us. All right, I'd like to talk to you a little bit about possible paths when we approach a communication problem challenge. So one point to have in consideration is obviously planning factors. So we have to focus on what is the message that we have to transmit. Sometimes people that do multimedia like us can get a little bit carried away with the cool stuff and the technology, but focus on the message. What is your target audience? You don't communicate the same way. If you want to transmit something to your peers, like we do sometimes posters or something like that, or if you want to transmit to, let's say, an audience of teenagers, it's completely different type of audience. You have to target the message to them and so on. Placement. What kind of medium are you going to use? Is it a planetarium like you have here? Is it something that will appear on TV? Is it a science center? So we have to have all this in account. And finally, the cost. What is your budget? Can you afford to do something pharaonic, or you have to be a little bit more modest? Second thing is information. Okay. This sometimes is the subject of some discussion with the researchers whose work we are trying to publicize. Because if you ask a physicist, what does an atom look like? Well, a physicist, of course, will perhaps try to tell you about atomic orbitals and how hybridizations happen and this and that. Okay. It's all very valid, but it really depends on the kind of audience that you are trying to target. If you don't have enough time for this, perhaps you should choose a different kind of path where you select your information. Imagine the case of the atom. This is a representation of the Rutherford atom, which is, of course, factually wrong. However, there's a lot of little tidbits of information just in that image that are correct. So there is a nucleus in the atom. The nucleus is composed of two different particles that there are in different colors. And there's this thing, the electrons, that are in some kind of organized trajectory around this. That's it. All of this is correct, and you can apprehend this information rather quickly. Then you could go deeper, but you have to target your information to the kind of audience that you have in mind. Another thing is the path of engagement. All right. So there is a buzzword that we hear a lot in the field, which is gamification. Gamification. What is gamification? Gamification basically is tricking your brain to use these obsessive compulsive impulses that we have in our reptilian brain to do certain types of things and try to use it for people to do some kind of action that you want them to do. And a lot of stuff nowadays uses gamification, right? You get badges, you get feedback, visual feedback for things that you think that you need, like likes in posts that you do in certain social networks. Things like that. All of these are processes of gamification. This is a way to engage people in a deep, long-term kind of involvement. But you could also choose the other way around, which is quick and fun involvement. Let's say I don't have time to give someone a masterclass or for a series of lectures or so on. I just have 5 minutes of their attention. What is more efficient? Probably the fun and quick way, where you engage them in a task. They get engaged in the task because the task on itself is fun, and on the process, you try to feed them some information and perhaps inspire them. Relatability. That's a very big one for me. We'll see it later. So, I'm sure most of you have taken selfies before. We all have committed that sin. And when we go on vacations and we take a selfie of ourselves, in front of the Eiffel Tower, I'm in Paris. Oh, here I'm in New York, in front of the Statue of Liberty. Oh, I'm in front of the Taj Mahal, here's my selfie, and you post it on Facebook. What you really want people to see on Facebook is not the Eiffel Tower and the Taj Mahal and the Statue of Liberty. What you want people to see is you. Because the most interesting subject in the world for almost everyone is themselves, of course. And this obsessive compulsive, this obsession we have with our self-image is something very powerful. And we thought for a long time, is it possible to use this for the good of science communication? Can we hijack this deep reptilian path in the brain to convey more efficiently something to the public? Turns out yes. We'll see more later about that. Okay, and finally, one thing we try always to do is balance the triangle between information that we provide to the public, to trigger curiosity. So sometimes the objective of an installation or a piece of media is just to get people to ask questions that before interacting with that, they didn't even know what to ask. And that's already a victory. That's actually a very good path to get them to talk to the researchers about what they are doing. And finally, very important, let's not forget that, entertainment. Let them have fun. Okay. So having said this, we made a kind of a chart, which we follow always when we consider a project, about some principles that we have to follow. So the first is that applications should be simple to use. And you should notice there the actual beta testers that we use. Our bar is really, really, really low. Things should be visually appealing. Visually appealing. And this, sometimes for my colleague physicists, is something that is, how to say, something we have to emphasize. Some of the tools that are used professionally by them are not appealing because that's not their objective. We need to do something that is appealing for the public. They need to want the sugar in that cookie to go there. How do you engage the public? Do you engage them because you make them get engaged? You're engaged because, or can you do it in a playful way? And finally, we try always to do things which are flexible, usable in a variety of scenarios. For example, if you do a project right now, perhaps in 3-4 years we want to use part of it again in something else, or perhaps a partner of ours, another institution, another university, wants to use part of it for a project they have, and we try to be as modular and open as possible. Okay, it's time to talk to you about some of the tools we have been developing over the years. These are not all, but there are some that I selected for this presentation. I start with TEV. So TEV stands for Total Event Visualizer, or Terry Electron Vault in physics language. Total Event Visualizer. This is a universal event display, which we built a few years ago, and this is the first universal event display which is really light. What is an event display for the physicists? When you have these particle collisions, you have like all these fluff balls that you see usually in the images, these tracks. This is called an event display. An event is the act of the collision and the formation of these particles, and you need to visualize it, you need to display it. TEV is a tool which is able to display these events from any experiment at CERN and beyond. Why is this important? Because if you go to, well, in the world of experimental particle physics, typically each experiment has its own type of data, databases, protocols, the description that they do of what is a track, what is a hit, is different for all of them. So it's really not interchangeable. Now, what we thought about was the following. You see, okay, you guys are British, I'm originally Portuguese, but let's say you were Chinese. We would probably be I don't speak Chinese, you don't speak Portuguese, we'd probably be speaking in English. So we would have a common intermediary language. So this is what we did. We created a common intermediary structure which defines everything you need to define about a particle event. So I don't care, I mean, if you have a track is a track. I don't care if it comes from experiment A or B or C. It's a track. They can adapt the parameters to that. That's it. And then we create the graphics tools to display and analyze this, because that's not the specialty of the physicists. Their specialty is to generate the data and to treat it and to statistically analyze it. So we created a tool for them to visualize this in a light way. More. So it works like this. We created this thing we call the TEV engine. Okay? And so there's a data translator that each experiment needs to translate to this intermediary common event structure. And then we have these operational classes, which what they do is they pick this common event structure and they display it, allow a track to be selected, whatever. And then from there we communicate with the world, whatever application you want. In fact, it works a little bit like this. It's as if you had a funnel and you put in one side the TEV engine and a user interface, because the TEV engine does not have the user interface. And then X, Y, Z, whatever features you want. And then in the other side, you get an application, which can be for a browser, for a mobile device, or for a desktop on a platform. So, since we started this project, it now became the official visualization tool of two of the major experiments at CERN, LHCb and Alice, more recently. And we also use it in other contexts. So we have special builds of this for the public. So here you see a bunch of examples where it was used here is with the Atlas experiment in a lot of science fairs. So here you have the former Director General of CERN giving a big interview, and what you see in the background is Tev showing live events of the Atlas experiment. Pretty powerful, you can say. These are live events, and I'm talking to you about what's happening right now at the LHC. Here are kids in a science fair in Chicago, interacting with the event display. See, it's ultra light, ultra easy to use. It's like a game, feels like a game. This is in the Frankfurt Book Fair. It's not really a book fair. It's a mix between a book fair and an amusement park. This is a science fair in San Francisco, and so on and so on. So, and speaking about the flexibility and multiple scenarios for usage of a product. So here you see it like this. Tev, I also told you that it's an official tool for the experiments, but we also use it in the pearl of our productions. So we'll talk a little bit more in detail now, which is the Lhc Interactive Tunnel. Now, the Lhc Interactive Tunnel, it's an immersive, interactive, augmented reality installation. Basically, well, the original one, the Mark I, was an installation that was built a little bit like a stage, was big, 6 meters by 6 meters by 3 meters height. We are now developing Mark III. We have 6 of this. So basically, you have 2 projectors here, which project to the floor. You have a video wall. You have 2 Kinect projectors here on the side, which detect. You know what are Kinects? Kinects are these devices made by Microsoft to capture the movements. Sorry, the movements of players in games doing their silly positions. It didn't have a great success in games, as far as I know, but they are amazing tools to use for interactive applications. This is one of our specialties. Is use Kinects for almost everything. It's like you guys drink tea, we use Kinects. So this system is powered by 2 high-end gaming PCs and has a router for communication between them, and with a tablet which controls the whole system. Now, we built this because in there we made certain games which work. So one of them is called Proton Football. Proton Football consists of this. Imagine that you have projected in the floor a virtual proton. You see it with its 3 quarks dangling, and you can virtually kick it. It's augmented reality without needing any device. You just augmented the reality of your floor, right there. You can kick it, and if 2 people kick it and make it collide, it generates a physically plausible event based on the physics of the Atlas experiment. Now, there's something amazing that happens here. That when people realize it, that what they are doing is not just generating a fluff ball, it's something else, they get really blown away. Here's what people are doing, really. When they collide these protons, I usually tell them this. You know what happened right there? It was magic. I know it's heretic to say in a scientific, to a scientific entourage to talk about magic, but you will agree with me in 2 minutes. It's magic, but it's not supernatural. Just imagine this. Imagine that you have a magic show. And you know that it's a magic show because there's a guy that has a tall hat. It's written there magic show, and you pay the ticket for it, so it's obviously a magic show. The guy gets his tall hat out, he gets a piece of cloth, he puts it inside the hat, says the magic words, right? Abracadabra, hocus pocus, and gets a rabbit out of there. What happened there? You have no doubt. Magic. One thing was transformed into another completely different. And my challenge sometimes to the public is, I ask them, so imagine you have something, let's say a car. You want to transform this car into a boat. How do you do that? And people go with all kinds of wild speculations. Oh, I insulate the car, and I put some floaters and this and that. You do whatever you want. I know what I would do. I would sell the car, and with the money, I buy a boat. It's very simple. There's an intermediary step here you didn't think about, right? Now, if you see a building, a garage, and you see one car entering in one side and the boat getting out in the other, from your perspective, it's like the magic that happened in the hat of the magician. one thing came in, another came out completely different, right? But now you know that there was a transaction that happened in there. The car was sold, and you bought a boat with the same money. So simple as that. Now, in nature, there's a way to buy and sell stuff, which happens all the time. And is described by the most famous physics equation of the 20th century that everyone has heard about, E equals mc squared. This just means that you can transform energy into matter or matter back into energy. Or in other words, it's as if you could use energy as currency to buy and sell matter. There are rules for this. I'm not going into that right now, but there are rules for this. But basically that's it. And that's exactly, it's magic, see, without being supernatural. That's what people are doing there. They are giving energy. You see here the number. This is the energy that people in gig electron volts, that people are giving to each of the protons. And when they collide, this energy is materialized into the mass of new particles that did not exist before and were created right there by the amazing power of E equals mc squared. Isn't this mind-blowing? I mean, when you see a fluff ball, that's one thing. When you have this experience, when you are doing magic, and it's totally legal, that's quite an experience. Now, you give a little nudge to the proton. You get just some particles, a couple of them. You give a big kick, right? I'm Portuguese. You play Cristiano Ronaldo on the thing, right? You get an LHC grade event. As you can see, we have even a hard time getting little kids out of this. Again, target your audience, but layer the information. So one thing is if you are in a graduate lecture about particle physics. Another thing is if you get a 5-year-old kid there, which probably is not going to understand even E equals mc squared, but is going to have fun. And probably his older brothers and his parents will want to know more about it. Then, of course, we have specialized versions of this. This is the Angry Birds version, which we brought to Finland. Finland is the country of origin of Rovio, the company that produced Angry Birds. And there was a protocol which was signed between CERN and Rovio. Don't ask. And they said, hey, can you do something that kind of symbolizes either? Yeah, sure. This is it. You're welcome. Great success with the kids. Well, this is me and the Henrique Carvalho, the other co-developer of the original lit installation with me. Another application we have there is called Ignite. Okay, Ignite is tricky. So we were talking before about the discovery of the Higgs boson, which happened in 2012. And all the questions. What is the Higgs boson and why should I care? Everyone was asking. And it's so difficult to explain. I mean, it's difficult for a physicist to explain to the public what is the Higgs boson. And it's difficult for the public to understand what the public is trying to explain to them. That's why we conceived an interactive, immersive experience where you can experience the Higgs field, all right? So the idea here is this. You have the screen divided in two parts. There is this thing called the Higgs field, which is what the physicists really care about. So the Higgs boson is just like a materialization of the Higgs field, but the Higgs field is what is really important. And now, you become a particle. You see yourself projected in there. You become a particle. And you can go between one side and the other, and you see what happens to you. Without the Higgs field, with the Higgs field. So the Higgs field allows particles to gain mass. But you see why. And there are a few interesting, odd things that happen while you are in the Higgs field. And people start asking questions. What is this? And why does this happen? And why like that and not the other way around? And that's it. Once we get them to ask questions, we got them. That's our objective. We engage them. We just got them. So this has been... Here it is, a bunch of kids, I think this was in Finland, interacting with the Higgs field. There is another aspect here. Remember I talked about the educational selfie? There you have it. People see their own silhouette projected there. It's their image. They get naturally attracted to that. You know what we see every time this goes any place? People get their picture in the Higgs field, and their Facebook profile picture next day is them in the Higgs field. And then they get their friends asking, hey, what is this? This looks cool. Hey, you just have to come to this exhibit and learn a lot of really cool stuff about something otherwise you would never want to know about. So this installation, we currently have 6 of them, and four of these 6 have been constantly traveling all over, I can say, the European continental plate. You see, from the Atlantic Ocean to the Caspian Sea, from the extreme north of Europe to the south of Greece. Last time I counted to 56 places, some of these places more than once. And this has an extra layer of interest for CERN management. You see, we talked before about target audiences. Okay, one possible target audience is the general public. There is another very special target audience, which is decision makers. This is the former Director General of CERN playing proton football with the Queen of Belgium.
There's the crown.
Well, she has a very beautiful blonde, natural blonde crown, let's say. This is another thing. VIPs, decision makers, people who sign the checks many times, they want to know what is it that you are doing. And believe me, if they get the experience to play like, they just release their inner kid. They just get engaged the same way that the kids do. And they start asking questions, but the good questions, because there's a problem with politicians sometimes, saying the good questions again, and this gives a tremendous vehicle for the researchers to let's say, to ride that horse and go in high trot right into their field and talk about their work, and also to another important thing, no offense to the researchers here, to help them focus on the message. Because sometimes researchers have the tendency, and I used to be one of them, have the tendency to get very carried away with the minutiae of their work and start getting very technical, and they can lose an audience, and this somewhat gives them a guideline to stay on message and to not lose the public. All right, so this installation is currently undergoing a big upgrade. So we are doing Mark III, and there's an upgrade both in the architecture of the installation, both hardware and the software. The software is all new, but also the applications. There are some new applications. So the first thing that you would notice now, if you would play with it, so this is me and our designer testing the new design at the Media Lab. This is our Franken tunnel, the bits and pieces of tunnel that are installed in the Media Lab for our testing. So the new design, I think, is gorgeous and has some extra features to make it even more attractive, such as, for example, you see here, there is a replay that is played of the latest kick. You know, so you kick, and we capture the player before he kicks. And so you see yourself 1 second before you kick and 2 seconds after, and we play it in slow motion. And you know, whatever you play in slow motion, when you are doing effort, looks epic. Just try it. Whatever you do in slow motion looks epic. So you can have the most unhinged guy there giving a kick, and it looks epic. Again, the appeal of self-image. Another thing is that, well, it's not very well visible here, but we have some gauges of the quality of the collision. Because you see, you have to aim, and you have to aim at the center. So we give you a measure of how far off you were, and we give you some incentive to do it right. But people will ask, so why should I do that? All right, so now you want to know about physics. Fantastic. We're glad to tell you all about the importance of aiming right a beam. Another thing that has been a topic of some priority for CERN lately has been to talk about applications of particle physics. So one thing that is very hot right now is something called hadron therapy. So hadron therapy, hadrons are protons, right? It's what we accelerate in these accelerators. Hadron therapy is that kind of therapy which is used for certain types of cancers, and that has been proven to be perhaps the most efficient kind of therapy for certain types of cancers. Basically, the advantage is this. When you have something like radiotherapy, so this is for the case of a brain cancer, something like radiotherapy, if you inside a beam from here, and you want to target this area here, so everything before the cancer is also affected and somewhat destroyed. And then, for the beam to be intense enough here to make some kind of effect, it needs to keep carrying on some of its destructive power beyond your target point. Now, with hadrons, it's a little bit different because you can tune the energy of the beam of protons you are targeting at the tumor, and have virtually zero absorption at very low depths, and virtually zero also much after the target. So you can in a much more effective way treat certain types of aggressive and difficult to treat cancers. Now this is a technology that is in part being developed at CERN. And they asked us if we could do an application to show people how that is made. So we made HIL. We are still developing it. In fact, the new tunnel, so the new proton football and HIL will be unveiled officially on November 10th in a big science fair where we have 1,000 square meters at the Palais des Expositions in Geneva. And so basically what we do here is we operate this gantry. That's the emitter of protons for medical reasons. And you can operate it, so it has a sci-fi-ish look. We got inspired a little bit by the Walking Dead and some sci-fi movies for the user interface. But you can get here, and so this is Carlos, our in-house designer, and he has his hands like this, and you see the projection of his hands exactly one-to-one on the screen, and he rotated the gantry in this direction. He could have done it in the opposite direction. So indeed you get there, and you can virtually operate the gantry, and then get to another post, and align it in another way, and then get to another post, just with your hand, get more or less energy, and see when you are right at the point, and then you clap your hands, and you have beams. So in an interactive and intuitive way, you learn how hadron therapy works. And again, this is a kind of augmented reality where you interact with a virtual a virtual device that is projected on your reality. There's also an accelerator in the floor. But you don't need any kind of device to operate it. You don't need to put gloves. You don't need to have special types of goggles or anything. You just step in there and you operate it. That's it. Okay, this is a completely different type of project. This is Impress. Is a presentation software. Impress stands for Interactive Media Presentation Software. It's a presentation software a little bit like PowerPoint or Keynote, but way more powerful, which we developed 5 years ago. And I know what you're asking yourselves. Why did you develop a presentation software when there are already so many in the market? I know. Well, let me answer you with a car analogy. Imagine the following. You have a specific need for your car, okay? So you need to go to really tough terrain to mud poles and pebbles and so on. Well, there are cars that can do that, all-terrain cars that can do that. What if you live, let's say, by the edge of a lake, and you are tired of going around the lake every day just to get the road that is on the other side? Well, it just turns out that there are also amphibian cars that can fulfill that need of you. You can just cut straight. What if you're a really, really, really fancy person and you want a flying car? Where are my flying cars? They are right here. Well, we can discuss about its usability and availability, but they exist. You know what does not exist? A vehicle that can do all of this at the same time. And that's the kind of vehicle that we need to transmit our message for the CERN visit point. So we built our own. We researched the features from the best presentation softwares in the market, what we really needed from them, what was accessory, what could we have done better, and so we built from scratch a full presentation software which now powers most of the visit points at CERN, which are visited by hundreds of thousands of people every year. So, a little bit about Impress. It's media-oriented, so we focus mostly on images, videos, and even interactive 3D scenes in the context of a presentation. It's interactive, as the name says, so it means it's not meant to be something static, like a PowerPoint presentation is. It's to have the public actually getting an input on what they're about to receive. It's non-linear. See, most presentation softwares are linear. So you go from slide 1 to slide 2 to slide 3. Sometimes you can do it with fancy transitions, but they are linear. Impress is non-linear. You can go from anything to anything. In fact, every slide works a little bit as if it were an application. So you can make anything be a trigger for any other action. It's multi-touch, I know. That's not a big deal today, but when we built this in 2012, there were not many multi-touch capable softwares. You will see why that's important for us later on. Okay, this is a feature that on itself deserved the build of a new presentation software, OSC communication. I don't know if you guys know what is OSC. OSC is a open sound control. It's a protocol, very old, I think from the 1980s, which was used for these MIDI keyboards that existed at the time to transmit information about, basic information about the notes. It just turns out that it's a very simple standard because basically you have to transmit text encoded in a certain way. And we implemented OSC in Impress. Why? Because this allows us to have a two-way communication between the presentation software and the outside world. So imagine the following, which actually exists, and I will show you examples. You have a presentation going on here, and you are in a room which has a few exhibit objects, and you have a presentation about the objects there. You press a button or an object there, and suddenly a physical spotlight in the room where you are illuminates that object. We just send an OSC signal from there to a controller that then turned on a lamp. Or the other way around. You touch the object, and automatically a presentation about the object starts in the screen right there. A sensor in the object sent an OSC signal to the software that knows that it should start a presentation about this. It makes, if you have enough imagination, it makes for really compelling visit spaces. Okay, 3D interfaces, so we can produce inside the presentation. We can put full 3D scenes with thousands of objects and make them all interactable. Like when you click on an object, something happens, whatever you want. Okay, this is a very special feature that there's a frame grabber that allows you to have external input from somewhere and include this as a window inside the presentation. So for example, you could have a webcam of someone somewhere else and make it part of a presentation. Web pages. We can have full interactable web pages, including with HTML5 content inside the presentation. COP, okay, this is a special feature too. The COP is the controller of the presentation. See, since these presentations are non-linear, you can easily get lost. Therefore, you need an omnipresent layer that allows you, for example, to navigate or go to to some quick links, and that's the cup. Multilingual support, so no need to do 10 versions of your slides, in English, Chinese, Klingon, Swahili. No, you just make one, and then you create languages, and you just say that this text is correspondent to this one in that language. It's very easy for us at CERN, as an international organization. We keep adding languages to some presentations to the public because we have pressure to do it, and it's very easy to do that. And finally, this is the mojo that powers the Impress, which is this mechanism called traction. Traction is trigger, action, traction. See? So the idea is this: you can transform. Well, you can have a trigger on any object for any action, which can trigger any action anywhere. For example, you can drag into a presentation a movie, for example. And a movie in itself is just an object that is there. It's not going to play. It's an object. It's like you have a file. Then you put an image file, a PNG, a JPEG, whatever, which looks like a play button. And you make a trigger out of click, which has an action here, and the action is play. Then you do the same for pause, the same for stop, and you just build a video player inside your presentation. Well, we are using this in multiple visit points at CERN, including, the first where we prototype a lot of this is the data center of CERN. So at CERN there is this data center which collects and processes all the data that comes from all the experiments, and it's very interesting, and a compelling presentation about that was necessary. So we built this special interactive multimedia room where there are physical objects here. There is this touch screen. This is like a giant iPad, 6 meters long by 2.5 meters high, all touch. It's running Impress. And then on the side here, there is a LED wall, which is also controlled by Impress. So we can make animations in the LED wall, which are synchronized with a screen back there. And we do this, for example, to explain statistics, to explain how data is collected, and so on. Then there is this glass, the main interactive glass, which is all touch. This is magic glass, which can be opaque or become transparent. And then you see, so when people see the presentation about the processing farm, then usually we invite them to approach the window, and they go with this opaque, and they get closer there and become transparent. They see, it's right here. All these I've been seeing the presentation about is right here. I'm above it right now. So SM18 is a special facility at CERN where magnets are prepared, cryogenically prepared, and we made architecturally beautiful and well integrated exhibit space. We have some real objects, and you can see in the back an Impress presentation that shows how they work interactively. Oops. Wrong button. There is the control CERN of CERN, where again, this is a magical window that can become transparent, and in the back, you would see the people actually operating all the accelerators. It looks like the NASA operations center, where you see like all these screens all around, but only it's for accelerators. And people, many times VIPs, get their induction at CERN here, and then we make this become transparent, and they see in the back, wow, and this is where the magic happens. And again, there are these objects, which you can touch them, and the presentation about them starts in the back.
So these are projections on the window?
These are projections, yes. So you see this piece of furniture here, that here there is a projector, here there is another projector, and they are edge blended here. Yes, these are projectors. So, and again, here you see the glass transparent, and this is the operations room. You see like the big control room that just became transparent. VIP talks. Imagine you have a head of state, UN ambassador, or whatever. And you want to really give them a compelling presentation. So this is the former Director General of CERN, Rolf Hoyer, rehearsing in Impress in this screen that we did a presentation for, I think, the Prime Minister of the Netherlands, I believe, in this case. So it's very engaging because we designed the presentation that he does so that he is kind of a showman. He likes to go around and talk and so on. So he goes and does this and then he touches back and something happened and he goes back and forth. So we spread the buttons in a way thought for him to give a show. But like, of course, in a way that is coordinated with him. It's very cool. And then, of course, there is the microcosm, which is the big science center, the biggest science center at CERN. There are many visit places. This is the biggest one right now. Microcosm is a very old science center. It has been there since decades. But very recently, we rebuilt it all. New design, new content, new technology. And inside, most of this is powered by Impress. Most of it. But not all. You will see some examples. Okay, this is not Impress, this is something else. And you will see some examples. This is very cool, I really like this. This is a set of screens, which we call Meet the Physicists, where we made so this room here is a panoramic photo of the actual control room of CERN, the one we saw before. And we see people operating there. And then you can choose, so this screen here is integrated with the designs, it's in continuity. And you can choose to talk to someone in that room that speaks your language. We have 5 languages that we support. And you pick your language, and someone, this is the German lady, she's actually Austrian, it's for the German language. And there's more, like here for the accelerator, there's a guy too. You see, this is at scale replica of the tunnel. And there is this guy here, this is Philippe Caillet. He is well integrated here, and he talks to you in French, this guy, about the accelerator and its operation. And in each room there is a theme, and there is a set of people that you can press the language, and they talk to you. They are at scale, like real people. They talk to you, and you can ask them about a variety of subjects, as they are pre-programmed, they were pre-recorded to talk to you about. It's very cool. People get, one thing I see people very excited about is that when they come from certain countries, they say, wow, I can actually talk to someone who works here and who speaks my language. This gives a kind of bonding, like national bonding, which is, for some people, is very important, some of the visitors. Okay, this is a crazy project, which is almost finished, but is already deployed, a beta. LSD. Okay, so we were asked to, so there's a zone in this microcosm exhibit where you have a mock-up of the dipoles at CERN, so these giant magnets, at scale. It goes in continuity with the tunnel there. And I was asked, hey, can you do something that lets the public have a trip through the different elements of the accelerator, how do they work, and have a vision of how all of this is integrated? We thought, trip, vision, it's called LSD. It's the LHC simulator dashboard. So basically what we do here is, so there is the accelerator in the back, but here, since you are in the environment of the control room, okay, if I go back, here you see that this is the control room, there's the guys working there that can talk to you in the control room. So you are now an operator in the control room. And there are 3 basic elements of an accelerator that you learn to operate here. So it's a game in 3 stages. First one is you need to accelerate particles, that's why it's called an accelerator. And for that, there is this thing called the RF cavities, radio frequency cavities. So radio frequency cavities basically, it's, well, in a very simplistic way, there are these structures where magnetic fields oscillate, and you get north and south reversed very quickly at the frequency as the beam passes, and it's like a swing. You keep accelerating it at each passage. So what we do here is, as the beams pass, you have to swipe the screen and whoop, you give it energy. If you fail, it starts losing energy, and if it goes under a certain threshold, game over. Try again. If you pass it, you achieve enough energy. Then you get to operate the dipoles. That's the next stage. So the first thing is accelerate the beams. Second thing is, okay, so we have a circular accelerator. How do we keep these particles going around a circle? It's not exactly a circle. A little secret between us is an octagon with very rounded corners, okay? Almost a circle. So how do you keep particles in track around this itinerary? Well, these points where there is curvature, there are these elements called dipoles, which pretty much push towards the center of this hypothetical circle the particles. And you have to tune up very well there's a very fine tuning for the magnetic fields here. So here you can do that. So you can use like in a cell phone, like more, less. And you see, here you don't see very well, but there are the magnetic field lines forming. See more, less. And you see the hypothetical track, well, here it's in green, which means it's in place, it's locked. But before you see it going straight in red, meaning zero magnetic field, zero deflection, then as you keep increasing, you start seeing the magnetic field lines, and you start seeing it deflecting more, like the hypothetical circle. If you do it too much, it curls inside here. So you have to get this fine point, and then that's it, it's tuned. And then there's the final stage when you squeeze the beams and you focus them. Anyways, we just deployed this about a week ago. And kids have been crazy playing this, and we're also collecting some data about the usage. So how long people take to each level, how many times they try when they fail, and so on, because we want to optimize the experience in the future. Okay, these are some of the selected projects. We have a lot more, but I'm already in almost 1 hour. So I'd like to talk to you quickly about what's next. So there's one thing. This is actually already 90% developed. Project CAPT. Just bear with me. CAPT stands for Connect, Acquisition, Processing, and Transmission. Doesn't seem very exciting like this yet. Just bear with me. Basically, what this is a node where we put a Kinect connected to a chip computer. And here we do the acquisition of the data, whatever it is. There's many things we can collect. And then we process the data here, and then we communicate with the world or other applications. Okay, this is actually done. Next step is the CAPT process. The idea is that you can put n CAPTs and connect them to the network to a machine that processes this data. And then you have a lot of information about a space. So a Kinect has about 4.5 meters of range. So if you wanted to, for whatever reason, cover a room like this, you would need probably 4 of them, 1, 2, 3, 4. And then connect to the Kino Pros, and I would know in every point in this room where everyone is, where is their head, even in which direction they are looking, where are their hands, where are their feet. Possibilities are tremendous. We'll get there. One of the possible applications of this, of course, CAPT is just CAPT and CAPT Pros. It's just technology. It's not an end product. It's just technology. This would be not an end product yet, but an intermediary product. Project JEDI. Joint Extension Distant Interaction. The idea is this. Have you guys ever used a laser pointer? Of course you did, right? I'm sure the first time you used a laser pointer, you had no trouble doing it. Right? It's very simple. You press a button, beam goes, there you go. And look at that. I can keep it relatively accurately in a small area, in a target at a few meters distance. And I'm doing this with a foreign object to my body. And we don't need any training to do that. But why do you use a foreign object to your body when you have a natural pointer which was born with you? You guys all have all fingers, right? So I have a 5.5 years old son, and when he was baby, even before he could talk, he would point at stuff, say he wants this, he wants that. It's a very natural thing for us to do cross culture. So what Project Jedi will try to do is using Kinect's cameras and image processing algorithms, identify fingertips accurately and map them in a 3D space. And you can say, okay, this is sure, you did some Photoshop there over a picture of hand, fair enough, but this is not Photoshop. Okay, so you can easily filter out backgrounds and identify fingertips using a Kinect in a pretty accurate way. And this was done with the previous generation Kinect, not with the latest ones, which are way better. And then out of this, you can try to identify the base of the finger. So you get the inflection points here. You get the bases of the fingers. You get the midpoint, and you project a vector out of this. And you can point at stuff in a virtual environment and interact with it. Think this is science fiction? Well, this is what has already been achieved. This was made. This is not ours. This is from a Japanese researcher that was interested in the same problem as us, with two little differences. Is that A, he was using an old Kinect, and B, we are going to use many CAPTs to improve the precision of this. So I believe that with just two CAPTs in a small space like this, we could have a pretty accurate reading of where someone is pointing. Another application of this may seem very simple, but the implications are tremendous. Is this project called Parallax of Objects to Viewer, or POV. The basic idea is very, very simple, is that you have a CAPT which detects the position of the head of a viewer, of a screen, this is a screen. And so you may have a 3D scene or something that adapts to the parallax of the person. And it may seem very simple. Technically, it's very simple, extremely simple. In fact, when here it is, we are in the Media Lab testing exactly this with a Kinect and a screen. But it's pretty, what's the word in English? It's almost uncanny. When you see an object that you know that it's in a screen, but when you move, the parallax moves with you, looks as if the object were there. Now, think about the implications of this. You can do cheap holograms with technology that you already have. More, we can do something else with this, which we are very interested in exploring in the very near future, which is have a different kind of augmented reality where you don't need devices that you are wearing or your cell phone or whatever, because when we ask the public to use their own mobile devices, we cannot control that environment. I don't know, is their phone really good or is it not capable of conveying an experience like we would like? Do they have internet connection or I don't know. So I don't want them to use their own devices. I want to give all the devices necessary. So when you are in a certain position or a range of positions that is the range of the viewer, the thing adapts to you. Now imagine this. Imagine you have a real object. In front, you put a transparent screen. Like, there are LCD screens which are transparent. We have some in the Media Lab, but it could also be a pepper ghost. You know, this pepper ghost is the simplest type of hologram. It's basically is a sheet of acrylic that is at 45 degrees, and you have a projector on top, and you see something projected in the air. Looks like a ghost. It's a very old technique, centuries old. But now, of course, with projectors and screens, we can do it much more cheaply and reliably. And you can put that in front of an object, and you could projection layers of information over it, adapted to the parallax of the viewer. Possibilities are tremendous. Okay, and this is my last slide. Without going in details, I'll just say a couple words about a few projects we have in mind. We didn't start them yet. So more or less, we have the technological base for all of them, actually. First is OmniTouch. OmniTouch, well, is the attempt at transforming any surface into a touch surface. Imagine this. This screen right here, it's not a touch screen right now. Why? Because there's no sensor here. There's no frame to capture my touches. It's not a capacitive screen, nothing. Now imagine the following. We would put a cap in here. The cap sees the screen. There's a projector. The projector projects 4 dots. And we calibrate. We touch 1, 2, 3, 4. So the cap knows the edges now and calibrates to this. From that point on, we can touch any point here, and it can transmit a mouse-compatible signal to the computer. So you could transform any surface, not even necessarily a vertical surface, into a touch surface, theoretically. Dynamap, well, you guys remember the Higgs field projection, where people were being projected a silhouette one-to-one behind them, well, stylized. Imagine if instead of projecting in the back, we had a projector in the front projecting over people. If you could do projection mapping, but dynamic. Imagine the following. You come in that space wearing a white suit. And suddenly, hey, you want to be Superman? I make you Superman. You want to be Batman? You're Batman now. So the possibilities in terms of storytelling are tremendous. I don't want to talk about charm. I just want to talk about God. We had a discussion about this before. It's getting very intense. God is the generator of dynamics. Very ambitious project. Picture this. You have a blank canvas, just with a few numbers, which are constants of the universe. Let's say the Planck constant, the fine structure constant, the gravitational constant, whatever. Suddenly you clap your hands and you have the Big Bang. You start seeing inflation, the first particles creating, right? The plasma of quarks and gluons, like the first hadrons, heavy particles forming, the first atoms. Then you zoom out, you see the clouds of hydrogen in the universe. They start coalescing and they start forming stars. They start nuclear reactions, stars. Then you zoom out and you see clusters of stars like this. And you see that they start getting a dynamic and rotating around. The first galaxies are formed. Then you zoom off and you see the macro structure of the universe, right? Okay. Congratulations, you just made the universe. Now you go back and you change these constants. And play it again, Sam. Now it's different. So to try to communicate to the public in a really, I think, mind-blowing, universe-blowing way, fundamental concepts of cosmology. So that's a project we really, really, really like to do, and it's in the back of our heads. Anyways, I passed my time, therefore, thank you very much.
That's great, thank you. So, we have time for a couple of questions.
Money.
Sorry?
Money. You didn't talk about money, but all this must cost quite a bit. So, can you give a ballpark figure, or maybe say where the money comes from? Is it just a part of the CERN budget, I guess? Or?
Yes. So we are, there have been so many restructurings at CERN. Right now, the Media Lab is part of the international relations sector, go figure. There is this group called ECHO, Education, Communications and Outreach. Inside this, there is a section called Engagement and, Exhibits and Global Engagement, and we are part of Exhibits and Global Engagement. Now, money. One thing is operational money, like my salary. or the salary of the team. Another thing is money for installations. So money for installations, it can come from comes almost always from CERN, but occasionally we have special events for which we try to innovate and so create new content, new installations and so on. So these events usually have a special budget, and so we get it from this. In terms of how much it actually costs, the operation, we are actually, I would say, pretty cheap for what we produce, because we are a very small team, 5 people now, but it's like an accordion. It goes between 8 and 2, you know? And occasionally we get, as part of non-declared budget, other institutions that contribute with people. So for example, there's universities that send us their students that are in related fields of studying multimedia or computer science, whatever, and we give them a really cool environment, really cool project. The universities pay, but we give them the experience, we give them the cool projects, and we give the logo of the university in the project. So it really depends when it comes from.
A couple of years back in the UK, there was a kind of a travelling exhibition about CERN, and again it looked wonderful, but very quickly it broke down continually. You know, it wasn't very robust. How robust are these kind of exhibits in terms of lots of little kids touching and kicking?
So I'm glad you asked that. That's a real concern. Lots of kids touching and kicking and interacting with stuff. That's why in the last few years we try to deal with distant interaction as much as possible. Hey, kids can kick virtual protons as hard as they want. They are not going to break the air. That's just fine. It may happen eventually. It has happened in a couple of occasions. As if you remember the map I showed of the places where this interactive tunnel has been, it has happened in a couple of occasions that we got material damage, but almost invariably, the material got damaged by the people in the exhibit that mishandled it when assembling, not by the public. Anyways, it's wear and tear. It happens.
Okay, I guess I'll end the formal questions now, and we'll thank you again. But if you want to ask an informal question or just hang out for a bit, have a chat about any of the technology or any of the issues, we'll be here for a while. And any members of the group who want to go for dinner tonight, let me know, please. Okay, let's thank you.